How's it going, guys? This is Chris McCormick, and it's time for episode 3 of my BERT Research series. So I know it's been a while since the last episode. I apologize for that. Took some time off around the holidays, but I'm back at it now. And in the last episode, we looked at the BERT tokenizer. We saw how it splits text into tokens and then how it handles words that aren't in the vocabulary by breaking them down into subwords or individual characters if it has to. And we talked about the basics of, what a word embedding is. And then we just kind of explored what's in the BERT vocabulary. So in this episode, we're going to now apply BERT to an actual application. We're going to fine-tune it on a text classification task. So the goal is just to get a feel for what it looks like to apply BERT in practice. And we're also going to learn, a little bit about the internal architecture of BERT from this. But that's going to come more in the next episodes. And in fact, I think, starting with episode 4, the focus is going to shift to how BERT actually works. So I'm looking forward to that. And I think it's coming along well. So you may have already seen on my blog that I've got a post on fine-tuning BERT. So let me give you a little bit of the backstory there so you know what you're looking at. For the past couple of years, I've had the pleasure of working with Nick Ryan. He is a contractor and an NLP expert, and he's been helping me with researching and understanding BERT, and then also writing some of the content that's up on the blog. So back in July of this year, Nick and I published a post on fine-tuning BERT, and since then, Hugging Face has changed the name of their library to Transformers to make it more generic, I think, to all the different transformer architectures that are out there now. So I took the opportunity to review the post, kind of reorganize it, add some more insights, simplify some of the code, and of course, update it to this new interface. So what's in that post, now that I've republished it, is the same as what you're going to learn in this video right now. Fine-tuning means taking a model that was trained on a large amount of generic text and then doing just a little bit more training with our application-specific text. So let's take a minute to review why fine-tuning is valuable and why we'd want to do that. BERT was trained on a really large corpus of books, and I think Wikipedia by Google. And from that training, we have a model that understands a lot about our language, about English or the other languages that they've trained models for. And that's going to benefit us in a few different ways. So if you don't use BERT, you're probably going to have to spend some time on R&D. You're going to have to try out different solutions to your task, probably do some engineering to try to make those solutions as effective as possible. But with BERT, you can potentially just take this model right off the shelf, do a little bit of fine-tuning, and then have something that delivers great results. So it can definitely reduce development time. And then training data is always a problem for us. If your application has very limited training data, then that's going to kind of force you down one of two paths. Either you're going to just kind of have to accept the training data as it is and accept lower accuracy, or go down the potentially very expensive path of trying to build a much larger data set that you can train on. So with fine-tuning, we can potentially train BERT with a lot less data. And finally, BERT may just be better than whatever you could come up with. So BERT is, and the other transformer models right now, are benchmarked on a range of different NLP tasks. And the previous state-of-the-art was different models that were trained specifically for those tasks. So people had worked very hard to build custom models that performed well on those benchmarks. And now all those tailored solutions are being outperformed by these generic transformer models. So it may just flat out give you better results. So those are some pretty compelling reasons to do fine-tuning with BERT or any other transformer model. There are a few caveats and limitations, so let's look at those next. As you might have guessed, BERT is a very large model. It consists of an embedding layer, which has 30,000 tokens mapped to embeddings which have 768 values each. So altogether, the embedding layer has about 24 million weights. And then beyond that, it's got 12 transformers stacked on top of one another. Each of those transformers has about 7 million weights, so altogether 85 million. And so the total model has a little over 100 million weights in it. And since the parameters are stored as 32-bit floats, this translates to about 400 megabytes in memory or on disk. So it's pretty big, and that has a couple implications. The fine-tuning is slow. Even though we're just fine-tuning, we're not training it from scratch. It's still relatively slow. In the example notebook that we're going to be playing with, we'll be using a GPU to train it, and we're only going to train it on 10,000 sentences, and we'll do that for 4 epochs, and it still takes at least 10 minutes, depending on what class of GPU Google gives you with your notebook. And likewise, it also has relatively slow inferencing. So when you want to actually apply, run BERT on some text, it's relatively slow. And something interesting was back in September of this year, I attended a talk given by some researchers from Twitter, and I forget what their application was, but something that stuck out to me is that they mentioned that they tried BERT, but that it was prohibitively expensive to run for their application. And I think the reason for that for Twitter is that they've got such a high throughput of text that they have to process. So it's not exactly fast. Research is being done to address this problem. There's a technique called distillation. And this is where you try to remove as many of the weights as possible from the model while still retaining most of the accuracy. So for production and trying to cut down on the cost, distillation is one option. The next problem is all of the domain-specific language out there, or jargon. So if you or I were to pick some random company and go sit in on one of their meetings, I think there's a good chance that we wouldn't be able to follow what's going on, because they'll use so much language that's really specific to their industry, or maybe even just really specific to their company. So I'd like to understand better how big of a problem this is. I can't make any sort of general comments about that yet. I know that it is an issue. Hopefully I have more to say about it, though, I guess, as we go on. And then finally, I think it's important to recognize that BERT, we talk about it being applicable to a wide range of NLP tasks, but it's not used for all NLP applications. So again, this is something I think would be worth going into in more detail later on, but I'll give you kind of a quick summary. So it can be applied to classification, like we will in this video. Also named entity recognition and part of speech tagging. And then you can also use it for question answering. It's a specific kind of question answering, though. It's not, it's not like Alexa, where you can ask it a question and then BERT will generate the answer for you. Instead, what it can do is that you can give it a question, and then you can give it a passage of text, and then it will do its best to predict whether that passage of text addresses the question that's being asked. So it can help systems that try to answer questions by pointing you to pieces of text. So those are things that it can do. On the can't do list are language modeling. And a language model is something that can tell you the probability of a particular sentence occurring, or the probability of what the next word in the sentence is likely to be. And so BERT is not a language model, so it can't be applied to that. And so it doesn't do text generation or translation. We're ready now to dive into the notebook itself. So I will put the link to this notebook down in the description for the video so you can follow along as I go through it. And it starts out with some insights about BERT and the advantages of fine-tuning, but we covered that in the slides, so we can go ahead and collapse the introduction and skip on to the actual code. So maybe a quick overview here. We're going to be using the Hugging Face library, so we need to install that. We need to hook up a GPU to our notebook. We're going to use the COLA dataset, so we need to download and extract and parse that. Then we'll look at how we prepare that text for BERT and construct our our training and validation dataset. Some insights here about fine-tuning. Then we'll actually get into the training. We'll do the fine-tuning of the model, and then we'll evaluate it on the test set for COLA. All right, so working with BERT definitely warrants the use of a GPU. And fortunately, Google will actually provide one for you for free. All we have to do to take advantage of that is to go to Edit and then Notebook Settings. And then in this Hardware Accelerator dropdown, just make sure that you've got GPU selected. So once you've done that, this next cell will just kind of check to make sure that, yes, we do have a GPU hooked up. I think we can ignore that message about TensorFlow for now. And then in order to run the code with the GPU, we need to be explicit with PyTorch. We need to tell it that we're going to use it. So this cell will do that. And it's also going to print out the name of the GPU that we've been given. And previously, Colab's been giving me a Tesla K80, but just in the past few days, it's been a Tesla p.100, which is pretty cool. It's a much newer GPU than the K80s. So I don't know whether that's a permanent change that they've made or it's based on availability or what, but it definitely makes a difference in the speed of this notebook. All right, so we're going to be using the Hugging Face library named Transformers. The Transformers library is pretty popular. You can check it out on GitHub. It's got 18,500 stars right now. Let's go back to the notebook. So we will need to install it with this command. And while that's downloading, a little bit about this Transformers package and what's good about it. So it provides an interface not just for BERT, but also for other transformer models that are out there right now. And it supports both TensorFlow 2.0 and PyTorch. And the main thing that it's going to give us here is that for whatever your specific application task is, they have a class that constructs the architecture for you for that. So specifically, we're going to be using the BERT for sequence classification class. And the code in this notebook, just so you know where it's coming from, comes from this run glue script from Hugging Face. And if we take a look at that, yeah. So this is a nice script. It lets you run these different transformer models against the glue benchmarks. And that serves as kind of some nice example code for showing you, how to apply these models to the different tasks in the glue benchmarks. The problem is, it's very configurable, and that kind of impacts the readability a lot. So here you can see that it supports running the benchmarks with a number of different transformer models: BERT, Roberta, XLM, XLNet, DistilBERT, Albert. There's a cleaner list of that there. And, it also supports single versus multiple GPUs. So you'll see these, these if statements like, well, if the number of GPUs is greater than 1, then you've got to do something special. It also supports 16-bit precision, like here. So there's some special code handling for that. Yeah, and then there's even some special code for the different models. So what I've done in this notebook here is to simplify it down a lot. So it's not not configurable, but it makes it easier to understand what's going on. All right, I zoomed in some on the video, and I'm hoping that will enable you to read the text without forcing you to go full screen on the video. So let's talk about the data set that we're going to use. We're going to use the COLA dataset, Corpus of Linguistic Acceptability. This is a relatively new dataset, came out in May of 2018, and it's one of the tests that's included in the GLUE benchmark. And it's actually a relatively small dataset. There's only about 10,000 sentences in it. And when I think about text classification, what comes to mind for me, and maybe this is just because of my limited experience or something, but I think of like trying to categorize text, like figure out what topic the text has. Either that or maybe like sentiment analysis, figuring out whether the text has a positive or negative sentiment. This is something very different. What we're going to do is we're going to feed these sentences to BERT, and BERT has to try and predict whether the sentence is grammatically correct or not. So let's go ahead and download this data set. We'll do that using the wget tool, so we'll install that first. And we'll download the zip file. And unzip it. Cool. Goes into our file system here. Put it under this folder, COLA public. So you can see from the folder names here that there's a raw version and a tokenized version. And we need to use the raw version. We can't use the tokenized version. The reason for that is that, we learned in the last episode that BERT has its own tokenizer, and it's critical that we use that tokenizer. We can't rely on a different tokenizer. So we will load the training data from the raw version of the dataset and print out, 10 random rows. Few properties here, but the ones that we care most about are the sentence itself and then the label. So 1 means yes, it's acceptable, 0 means it's not. Heidi believes any description of herself. That's fine. John leftant, the party early. Okay. Or we talked about that he was sick for days. Yeah. Really, the only 2 columns that we care about from this data set are just the sentences themselves and their labels, whether they're grammatically correct or not. So we'll just pull those 2 columns out of the table, the sentences and the labels. And then in section 3, this is going to be all about how we prepare that data set into the format that we can use to fine-tune the BERT model. And BERT has some very specific formatting requirements, so it's worth talking through these. Now, in the last episode, we already talked about the BERT tokenizer. So we know that in order to use BERT, we've got to use the tokenizer that comes with it. The basic flow is that the tokenizer splits the sentence into tokens or into subwords if it needs to. And then each of these tokens or subwords has a unique vocabulary ID that we need to map it to. So those same steps still apply, but there's a few important details that omits. All right, there's 3 main requirements that we need to implement here. First is that BERT expects for every sentence that you give it, it expects a special token at the start of the sentence and then another special token at the end. And then we can give variable length sentences to BERT, but they all have to be either padded out or truncated to all be the same length. So we need to do that as well. And then something that feels, kind of redundant to me, but is a requirement, is that we have to specify this thing called the attention mask, which is really just an array of ones and zeros. And it has a 1 in it for every token that's actually a token, and then zeros for the padding. So we'll take a look at that here in a second. All right, so starting with the special tokens, these are pretty interesting. At the end of every sentence, we need to put this SEP token, and that's literally what it looks like with the brackets. And this comes from BERT being trained on 2-sentence tasks, where you can actually give BERT 2 sentences, such as like in question answering, you could give it 1 sentence which has a question in it, and then the other sentence can be like a piece of a sentence from a book or something like that. And the BERT model has to say whether the question in sentence A can be answered by the information in sentence B. So when you give it 2 sentences like that, you put a separator token in between them. So it makes sense to me there. You still have to do it even if we're only doing a single sentence task like we are in this example. So I'm not entirely sure why that's the case. My best guess would be that that the model was trained that way, and so that's SEP token, the separator token, it's in there, and BERT expects it to be there, and it's all of its whatever logic it's encoded into its weights depends on that token. So hopefully we'll learn more about that and we'll have more insight. The other special token is the CLS token. It stands for classification. So for any classification tasks, this needs to be prepended to the start of the sentence. And this token actually has some kind of special significance. And to see what that is, it helps to look at the architecture of BERT a little bit. Let's say we've got the sentence, "I like to draw." So we need to add the SEP token at the end and the CLS token at the beginning. And BERT consists of 12 of these transformer layers, all stacked on top of each other. And when we start out, we've got our list of tokens, and each token has an embedding in the embedding lookup table. And there's even, there's an embedding in there for CLS and one in there for SEP too. So we look up the embeddings for all of the tokens and then feed them into the transformer. And then on the output of the transformer, it actually outputs the same number of vectors as the number of tokens that we fed in. So every layer takes in this set of tokens and takes in this set of embeddings, and then outputs another set of embeddings that presumably have been modified and enriched in some way by that by each transformer layer. And when we get to the final layer and we want to do our classification, we ignore every embedding that comes out here except for the one corresponding to the CLS token. So just this one embedding goes into our classifier, and then we make our predictions based on that. Yeah, so that in the paper it says that first token is always CLS, and then the final hidden state corresponding to this token is used as the aggregate sequence representation for classification tasks. So everything that it knows about this sentence all has to be encoded into this vector right here. And then the classification decision is made based on that. And something I'd like to understand is why do that? Why not pool together in some way all of the vectors? But I'm sure they care a lot about their standings on the benchmark. So I'm sure if pooling were better, they would have done that. So there's got to be a good reason for this. And I think it also makes sense to me that if the model is trained this way, if it's trained such that the only the CLS token is fed into the classifier, then the model is going to be motivated to encode all the information it needs into that one vector. The other requirements are the sentence length and the attention mask. So BERT has 2 constraints around the length of our sentences. First, they've all got to be either padded or truncated down to a single fixed length that we get to choose. We get to pick what length we want to use. But BERT also has a maximum sentence length of 512 tokens. So whatever length we pick, it's got to be less than or equal to that. And then to do the padding, there's actually a special pad token, PAD, and it's got its own embedding in the vocabulary. And for the sake of this illustration, let's say we want to pad all of our sentences out to 8 tokens. That's pretty short, but good for the illustration. So we would add, there's 6 tokens already in the sentence. We would add 2 more pad tokens. And then this attention mask is, just this array that has 1 spot for every token. And in it, we just put a 1 if the token is a real token and a 0 if it's a padding token. Now, something I was kind of curious about, and I've looked into a little bit, is whether these pad tokens are actually incorporated into the model or into the model's decision making. And it looks like yes. I tried running this notebook twice, once with a max length of 64 and then again with a max length of 128. And with the length 128, the training took longer and the score was lower. The scores you have to be careful about because for this data set, the score can vary a lot just with different random initialization. So I wouldn't necessarily assume that that this is really like a better choice accuracy-wise. Maybe it was, but I wouldn't assume that right away. Anyway, so these two things imply to me that that yes, the padding tokens are actually computed on, and they're in here, and they go all the way through the 12 layers. That's it for the requirements. Now that we understand those, let's go ahead and just blast through the Python code that actually applies those requirements to the data set. We're going to use this function tokenizer.encode, handles a number of steps for us. It's going to split, for each sentence, it's going to split it into the tokens. It'll prepend the CLS token and append the SEP token for us. And then it'll map all those tokens into their vocabulary IDs, the integers that represent them. And something a little curious to me about this function is that it includes support for truncating sentences to a maximum length, but it doesn't support padding. It seems like kind of a strange omission to me, so I'm curious to look into that more. But for now, we're going to have to do the padding separately. So we'll run this cell. And then there's just an example. So there's the original text. It's been broken into tokens. The special tokens have been added. The ID for the CLS token is 101. And then the ID for SEP is 102. So we can see those in there. All right. So next we need to do the padding and truncating of the sentences. So to do that, first it's helpful to know what's the maximum sentence length. And note that this is we're not doing the sentence length based on the original sentence string. We're doing it based on this token IDs list. So the longest sentence in the data set is 47 tokens. So I'm not sure the best way to choose a maximum length based on that. I chose 64 because it's close to 47 and it's a power of 2. Have to learn more about the pros and cons of making this bigger or smaller. So with that choice made, I'm going to use a helper function from Keras to do the padding for us. And the tokenizer actually records what the pad token is and what its ID is. So we can print that out just to make sure we have it right. Other models, I think, maybe use different tokens for padding. Yeah, so the padding token is pad and its ID is 0. And great. Now all of our training sentences or all of our dataset sentences have been padded to 64 values. And then again, the attention mask is just a Python list basically where we go through every sentence, and for each token, if the token ID is not 0, then we put a 1. And if it is 0, we put a 0. Great. Okay, and then for our training loop, what we're going to do is we're going to split the development set into 90% for training and 10% for validation. So to do that, I'm using this helper function from scikit-learn, train test split. Set the test size to 0.1, so 90% and 10%. We'll set the random state because we need to call this function twice. We need to do it once on the vectors and their labels, and then again on the masks. And we want them in the same, we want the same random selection, so we need to use the same random state between those two calls. All right, so now we've got our data set divided into training inputs and validation inputs, along with their labels and their attention masks. The last step in preparing our data set is just to convert the data into the format that PyTorch expects it. So all of the NumPy arrays in our data set, we need to convert into torch tensors. And then we're also going to use this helper class from PyTorch called the data loader. When we do our training, we're going to train in batches of training samples. And the data loader is just going to handle that batching for us. It's also, as I understand it, helpful for managing memory requirements, though I think with this COLA data set, it has fewer than 10,000 sentences. Memory is probably not really an issue. Okay, so that's everything we need to get our data set ready to train. I'm going to stop this video here, and then in part 2, we'll actually go through the PyTorch code for training the BERT model. So I look forward to going through that with you guys.